Hi, this is Barrett Givens, and in this video, I want to talk about the subspace topology on surfaces in R3. So let's say our topological space X is R3, and let's let Y be some surface. So there's lots of different surfaces that we could have. And we want to think about what is the subspace topology. Well, for the subspace topology, sets are open in the subspace topology if they have the form of being a set that's open in X intersected with Y. Basic open sets in R3 are three-dimensional open balls. So like spheres without their boundary. Okay. So imagine like a tomato, but with its peel ripped off. Okay. That's a basic open set in R3, big 3D open balls. And so let's look at an example. Let's say that we have z equals x squared plus y squared. I have a typo there. Z equals x squared plus y squared. That looks like a paraboloid. So it's just the surface of the paraboloid. It's not an inside, it's just a surface. And imagine I take an open ball, I take a big 3D ball and intersect it with that surface. What will I get if I take a big 3D open ball and I intersect it with that surface? I claim that I'm going to get something that looks sort of like a circle, like as the ball kind of goes in there. If the ball were to come up directly from below, it would sort of intersect this on this sort of cap down here at the bottom. Okay. If it were to come kind of from the side, then it would sort of look like this and then like continue around to the backside. So they're basically just going to look like what you would take if you just like cut holes out of your surface and then didn't include the edge. So those would be the basic open sets on this subspace topology of this surface. So it kind of looks like, the open sets in R2, the open sets in R2 look like open balls like this, but we've just taken R2 and we've kind of folded it up or something. Okay. A particular very important example is the torus. Okay. And I claim that the torus has this equation, r minus 2 squared plus z squared is equal to 1. And that is in cylindrical coordinates. So we're doing cylindrical coordinates here. So there's like a theta that is missing. Okay. Cylindrical coordinates. So let's think about, first of all, why is that an equation of this torus or donut that I have drawn here? Well, if I think about the graph of r minus 2 squared plus z squared equals 1 on just an RZ plane, this looks like the equation of a circle. And it's a circle that's centered at the point 2 comma 0 and then has radius 1. So it looks like this. And that's for r. So r here in cylindrical coordinates, r is like the distance from the origin. So it would sort of look like this in the x direction and this in the y direction and this in the xy, 45-degree direction. There's no theta in this equation, which means theta can be anything. So if I were to think about kind of like um, XYZ axes here, okay, it would take this circle that's up here at the top and then have sort of a copy of it for every possible theta. And so like I've drawn sort of one example of the circle right here. That's this circle. But there would be one at every sort of like at every possible theta. Okay. So that is the equation, or that is one equation of a torus. This particular torus happens to have the circles that you get if you were to slice right there, they have radius 1. And the distance from the origin to sort of like the inside, the hollow core of my donut is 2 units away. Okay, so now that we've gone through all that, let's also talk about what would the open sets in this subspace topology look like. So again, imagine taking a big 3D ball, a big solid ball, but without its boundary, and kind of moving it through this torus. As it moved through the torus, what would its intersection with the torus be? And the torus, remember, is just like the sort of surface of the torus. It's a hollow torus. It's a hollow donut. It's quite disappointing. And so I claim that it would just look like sort of like circles like lying on the surface of the donut. Okay? Circles lying on the surface of the donut. So the open sets would look like circles lying on the surface of the donut. And it's kind of like, as we said before, in R2, the open sets look like this. So these are going to look just the same sort of thing, except that they're like, they're like the melting clocks in this famous Salvador Dali painting. They're circles, but they're lying on a curved surface, so they've kind of gotten a little morphed, okay? And just in general, any open set on the surface of the torus would just look like any sort of pancakey kind of shape, could be very distorted, but not including any of its edges. And that's because in R2, that's because uh, I'm just going to leave it at that. I'm not going to necessarily over-explain why. Okay, and so this is the torus. We also call this, for reasons that we will see later, we call this S1 cross S1, the circle crossed with the circle. And this is its subspace topology that it inherits from R3. Okay, thank you for listening.